Hello and welcome. My name is Peukert. I'm a postdoctoral researcher at the ARC Training Center for Integrated Operations for Complex Resources. Today I'll be talking about my research investigating sensor simulation for improving ore sorting. My research project is focused on optimizing sensor-based ore sorting to divert waste prior to being sent to the mill and further processing. My research is designed to work with the other projects at the Training Center in order to deliver integrated solutions for the overall problem of processing complex resources, from exploration through mining through to mineral processing. The key points that I wish to discuss today is that sensor modeling can help implement and enhance sensor-based sorting. Today I'll be presenting my research developing a model of a prompt gamma neutron activation analysis or PGNA sensor that can accurately simulate the sensor response. This developed model can be used to help implement sensor-based sorting, as the model can simulate the response for a broad range of conditions, enabling fast and low-cost evaluation of new applications. Additionally, the simulations can be used to investigate enhancement of sensor-based sorting techniques by providing additional information and investigating new sensor designs and analysis techniques. Why is sensor-based sorting essential? The key issue to be resolved is growing global mineral demand. As shown below, a growing global population and the transition to renewables using an energy source that is far more mineral intensive is forecast to significantly increase mineral demand in the coming decades. In order to meet this demand, lower grade deposits of ore will have to be mined, which will require the processing of large tonnages of ore. Processing this ore using traditional methods would be costly and consume great quantities of electricity, water, and chemical reagents, and produce large amounts of fine waste to be stored. A key solution to overcome this problem is the use of sensor-based sorting. Sensors, such as the GeoScan sensor from partner organization Scantech, can provide information in real time on the processed material, such as the elemental composition of the ore, and this information can be used to classify the processed material as either product ore or waste. This classification can then be sent to a physical sorting system, enabling the removal of waste prior to further processing. And this can reduce the costs, reduce water and electricity consumption, and reduce the production of fine waste, limiting the requirement for tailings storage, as well as coarse waste being a useful byproduct. To deliver sensor-based sorting, a key approach is sensor simulation. This is due to the fact that a mining operation is a long-duration project requiring vast investment, which has long lead time and cannot be easily changed. Understandably, mining companies are thus very conservative about adopting new technologies unless they are confident that will work for their given application. Developing a simulation of a sensing technique can enable modeling of the sensor response for a given use case to help provide the confidence to proceed with acquisition and implementation. Additionally, sensor simulation can provide additional data, reducing the requirement for physical test work and aiding calibration. Simulations can also provide data such as separating the signal from noise and the sampling distribution that cannot be easily measured and can inform development of new sensor configurations, use cases, and analysis techniques. My research has focused on the development of a prompt gamma neutron activation analysis sensor model based upon the GeoScan sensor from partner organization Scantech. This simulation was developed using the GANT4 Monte Carlo toolkit. GANT4 was selected as it is capable of modeling the complex geometries of the sensor and a broad range of sample materials, and contains a vast library of physical process models, and is capable of modeling nanoscale depositions for medical physics through to high-energy particle physics depositions. The simulation is capable of modeling the full physical interaction of the prompt gamma neutron activation analysis sensing process, from the interactions of the neutrons emitted from the neutron source, the resulting characteristic photon interactions, and the transport of these characteristic photons to the detectors within the sensor. A series of corrections were then derived in order to convert the photon flux reaching the photon detectors to what is physically measured by the detector, and this provides an ideal combination of accuracy, computational speed, and being able to provide additional information. The detector response function is the first of the derived correction functions. This accounts for converting the photon energy flux incident upon the detector crystal to the energy deposited within the detector crystal. The activation photons produced in the sensing technique have high energies and can often transit the crystal without depositing the full energy. In order to account for this, GN4 was used to model the energy deposition within a detector crystal for a broad range of initial photon energies corresponding to the measurement window. The energy deposition spectrum for each initial energy was recorded, as shown in the figure below, for the functions for 2 to 10 MeV photons. The resulting response function was used to convert the flux to the energy distribution. The second correction function accounts for differences between the energy deposited in the crystal and the energy recorded by the detector. This is due to the fact that the measurement of the energy via fluorescence, amplified by a coupled photomultiplier tube, and the measurement electronics has a degree of uncertainty with a Gaussian characteristic, and therefore this uncertainty can be corrected for by applying a Gaussian peak broadening function to each of the recorded peaks. The energy-dependent width of this Gaussian function was extracted from geoscan measurements. The application of the function is shown in the figure below, where we can see that for higher energy photons, a broader peak spread is applied, reducing the strength of the central bin and widening the spread function. The final correction process is accounting for the energy peaks. The peak activation peak distribution for iron 56 is shown below. The exact integral energy levels of the nuclei are not known, and therefore to ensure energy conservation, the GN4 models model just the energy deposition of the highest peak. The low energy peaks are implemented by normalizing this peak according to its relative strength from the library spectrum and introducing the lower energy components. Combining the derived correction functions, it is possible to accurately model the PGNA spectrum. The simulated spectrum for an iron oxide sample is shown in the figure on the right, for the simulation with and without the peak correction in blue and red, compared with the geoscan spectrum in black. Overall, we can see that the general spectral shape is well reproduced within the simulation, as well as the absolute strength. The location, width, and relative strength of the main characteristic peaks is also well reproduced, and the main characteristic peaks are labeled within the simulation. We can see that the main iron peaks emitted from the sample are well reproduced, as well as their relative strength, as well as other peaks emitted from the sample from the sensor components themselves. We can see that all of the peak corrections combine in order to reproduce the general spectrum. The peak corrections reduce the overestimation of the highest energy iron peaks and introduce the appropriate strength of the lower energy peaks, matching the relative strength. The peak width function correctly models the width of the peaks. And finally, the detect response function helps to introduce the relative strengths. For example, the ion peak at 7 MeV is a combination of a primary ion peak and the escape peak of the primary ion peak. Note that oxygen peaks are not seen in the spectrum due to low neutron capture probability of oxygen. The combined correction processes enable a good reproduction of the geoscan spectrum, as seen by the relative difference being roughly centered on 0 below. The overall validation findings for a range of sample materials are detailed in the table below. Overall, it was found that the simulations were able to accurately model the geoscan spectra, while reproducing the general shape, strength, and characteristic peak position, relative strength, and width. This is a promising result and is able to achieve a close reproduction of the observed geoscan spectrum. Note that the median difference is lower than the mean difference due to a few peaks which overestimate the case. Full results are shown in the validation paper below. The next steps for my research is to work closely with industry partners to improve the sensor model to better reflect the physical sensor, and to work on implementing the model to evaluate applications for a broad range of industry uses, and to investigate improvements in sensor design and analysis. Additionally, models can be developed for additional sensing techniques to enable improved evaluation by combining results from multiple sensors to better characterize the material and improve ore sorting and control. Thank you to the research and industry partners of the Training Center, and thank you for listening.